In this video, I want to talk about the derivative as a function. Up to this point, we've been talking about the derivative at a point. So if you recall, if this is our point A, and then we move over a little bit, we add some to A, we call that amount H, then this would be A plus H on the x-axis. And so if we come up to the function, this is my function, f, then if we come up here, right there, that's my f of A. And of course, coming over here, then this point here would be f of A plus H, right? And so we said that if we have the secant line that goes through those 2 points, not very much of a line, but you get the idea, then the slope of the secant line is f of A plus H minus f of A over A plus H minus A, right? Because this point is A f of A, and this point here is A plus H f of A plus H. Alright, so you find the slope between those 2 points, this is what it looks like, right? Now we can simplify that to just f of A plus H minus f of A over H. That is the slope of the secant line. But if I let this H here, this distance, go to 0, that gets smaller and smaller so that the difference between A and A plus H becomes smaller and smaller, this interval, then we said, I get my other colors, then that's basically taking the limit, and we would end up with, the limit would be the slope of the tangent line. So if I put this limit in front, that's the difference between the slope of the secant line. So these are actually no longer equal, but this is the slope of the secant line. If I simplify and then take the limit, this is the slope of the tangent line, which we call f prime of A. It's the derivative of f at A, or the slope of the tangent line at A, or instantaneous rate of change at A. All those are equivalent ways of saying the same thing. So that's at one particular point A. Remember what we said about A is that A is fixed. A does not move. It's at one particular point we are getting the slope of the tangent line. So I'm going to draw a very similar, actually this one's probably getting a little bit tired, so let me use blue. Very, very similar graph. And this is a little bit subtle, so you have to kind of stay with me here. All right, instead of calling that A, I'm going to call it X, which means it could be here, it could be here, it could be here. A is fixed. It doesn't move once we define it. It could be 2, it could be 3, 5, 10, it could be over here on the other side, it could be negative, whatever. But it's fixed. Once we define it, it stays, and this thing just moves. X is going to be any random point in the domain. That's an important but subtle difference between the derivative at a single point versus the derivative as a function. So here, once again, if I take whatever my kind of variable point x is, and I'm going to add h to it, so over here I've got x plus h. You can see, so here's f, this is my x-axis, here's my y-axis. Here I have f of x. If I come up here, I've got f of x plus h. Everything looks the same, right? So if I draw in the secant line a little bit straighter than the last one, once again the secant line there is f of x plus h minus f of x. We know it's going to be, well, I'll just go ahead and write it, x plus h minus x. That will simplify to f of x plus h minus f of x over h. All right, but once again, if I let this h go to 0 so that this point approaches this point, then that is, we don't really have equals anymore, but if I just take that limit as h goes to 0, this is going to give me f prime of x instead of f prime of a. This will be a number. So when we're all done, we'll have a number, and that number will be the slope of the tangent line. Here, I'm going to get a function, which means that there is, not always, but usually there will be an x. It'll be a formula. It'll be another function. So I think you know, I can keep on talking about the difference between a and x forever, but I think that it might be easier to see an example, so, and we can kind of come back and think about what this would mean. So, for example, let's look at, I don't know, I think something simple might be square root of x. Simple enough that I can just kind of make my point rather than spending all the time doing the algebra. Okay, so let's say here we wanted to look at, you know, at x equals 9. We wanted to find the slope of the tangent line at x equals 9. All right, so, well, really this is kind of, now this is kind of our a, right? Because it's fixed. It's at, I mean, a is a specific value of x, and in this case it's 9. So we know, real quick graph, you know, square root of x looks like this. You know, 9 is going to be out here. We would expect the slope of the tangent line to be kind of getting kind of flat, but positive. All right. So if I use my definition, limit as h goes to 0, and this is going to be f of 9 plus h minus f of 9 over h. All right. In this case, f is square root, so it's going to be the square root of 9 plus h minus the square root of 9 over h. Well, that's the square root of 9 plus h minus 3 over h. And here, we're going to multiply by the conjugate. So we have the square root of 9 plus h plus 3 over the square root of 9 plus h plus 3. All right? So when we expand this out, we get 9 plus h minus 9 over h times square root of 9 plus h plus 3. Okay, well, of course the numerator simplifies just to h over h times square root of 9 plus h plus 3. H divided by h is 1. So now I'm taking the limit as h goes to 0. Don't forget, I did all the algebra in here, but don't forget we start off with a limit. So square root of 9 plus h plus 3. Now I can just plug in. You know, notice if I had put in up here, if I put in 0, I would have had the square root of 9 minus the square root of 9, which is 0 over 0. So we had to do some simplification here. At this point, I'm going to get 1 over. When I put in 0, I'll get square root of 9 plus 3. Of course, that's 3, so it's 1 over 3 plus 3, which is 1/6. All right, so that is the slope of that tangent line. If I wanted to do it, you know, say at 4, I'd have to do this all over again, and I'd have to change the 9 to a 4. Or if I wanted to do it, say, at 1, or at, I don't know, 12. That wouldn't work out so nicely because 12 is not a perfect square. But anyways, you get the idea. Every time I want to find the slope of a specific tangent line at a specific point, these are examples of A because they're at a specific point. All right? But if I wanted to, I can do this same thing, but I'm going to do it now for just some generic x value. Okay? So this will all look very similar, except instead of using a specific number like 1 or 4 or 9 or 12, I'm going to use x. All right? So, oh, the other thing, this is important, this was f prime of 9. Okay? So we did that with 9, right? This is what I mean by f prime of a. It's a specific number that goes in there. So f prime of x is going to be the limit as h goes to 0, and it's going to be, well, we already said f of x plus h minus f of x over h. All right, but now the only thing that I have that's specific now is f. F is square root of x. There is not going to be any a here because I'm looking at for any x value. So this is going to give me limit as h goes to 0 of the square root of x plus h minus the square root of x over h. Now I can't simplify this any further like I could up here. I could make that, I could reduce that to a 3. So I'm just going to go ahead and multiply by the conjugate. So the conjugate is the square root of x plus h plus the square root of x over the square root of x plus h plus the square root of x. I always have to do the conjugate over itself because this is equal to 1, so we're not actually changing the value of the function that we started into something else. Okay, if we multiply this out, that multiplied gives me x plus h. The outer and the inner are the same but opposite sign, so they cancel, and then negative square root of x times positive square root of x is just negative x over, And this is, again, remember, it's important to not distribute here. Leave these separate because we're hoping for some cancellation, which will be easier to do if we don't distribute. Okay, so here we are. Now, the x minus the x, that's just going to give me an h over h times that whole thing, which I won't bore you by writing all over again, but this, we're going to get the same cancellation we got up here. So this will be a 1. So now we're taking the limit as h goes to 0 of 1 over the square root of x plus h plus the square root of x. Now if I substitute, again, here, if I put in 0 for h, notice it would have been 0 over 0 again. So here I put in 0 for h. Now I'm good. I've got 1 over square root of x plus the square root of x. But that is 2 square roots of x. Okay? So here is f prime of x. Now notice at this point I can use this to find any of these. So if I know that this is f prime of x, so notice it's a function of x, right? As x changes, I'll get different values. So I could find f prime of 1. It'll be 1 over 2 times the square root of 1, which is 1/2. I could find f prime of 4, which is 1 over 2 times the square root of 4. Well, that would give me 1/4. Notice if I put in 9, like I did to begin with, I would take the square root of 9, which is 3 times 2, which would give me 1/6. That's what I got. All right. So, again, just to reiterate, kind of point out some things. F prime of a, in this case f prime of 9, gave me a number, right? F prime of x, down here we see it gave me a function. And that function now can be used to find the, so what this is saying is this is the slope of the tangent line at any point x in the domain of square root of x. All right, so at any point in the domain, so it won't work for anything that's negative because we can't take the square root of a negative number. In fact, it also won't be defined at 0. Notice here if I put in 0, this is undefined, but that's because I end up with a vertical tangent line at the origin. But anything else here, I can find the slope of the tangent line at any point x by using this formula and putting in the number for x. Okay, so that's just about everything. The only other thing I wanted to mention was just an issue regarding notation. So we've already covered this issue of f prime of a versus f prime of x. This is a number, and that number is the slope of the tangent line at a. This is a function that would give us the slope of the tangent line at any point x in the domain of f. All right, so some other notation you might notice or might see. So, you know, many times we call f of x, that's just our y value. So you could also see y prime, all right? Or if you just see y prime, then it's this. If you see y prime of a, like y prime of 2 or 3 or whatever, then you're talking about this. Another notation that you might see is called Leibniz notation, and it looks like df dx, or it might be dy dx, right? Because y and f are kind of the same thing. So, for example, you might see the derivative. The way you could read this is the derivative with respect to x of something like x to the 4th, and you might see a line with like x equals -2. So this says the derivative of x to the 4th evaluated at x equals -2. So this would give us the slope of the tangent line to this function at this point. All right. So just so you're aware of the different notations that you'll see in your text, I wanted to point those out.